This is for reassessment 10. In outer space are rocks whose mass is 3 kilograms and whose velocity was 3,900 in the x, negative 2,900 in the y, and 3,000 in the z meters per second, struck a rock with a mass of 13 kilograms and a velocity of 220 in the x, negative 260 in the y, and 300 in the z meters per second. After the collision, the 3 kilogram rock's velocity is 3,500 in the x, negative 2,300 in the y, and 3,500 in the z meters per second. What is the final velocity for the 13 kilogram rock in vector notation? So first we're going to start off with the momentum principle, where P total initial is equal to P total final. We then know that P of rock 1 plus P of rock 2 initial, these are both initials, equal to P of rock 1 final plus P of R2 final, which is our momentums. And then we can break up our P, so momentum equation is mass times velocity. So we have the mass of rock 1 initial plus the velocity of rock 1's initial velocity plus the mass of rock 2 and the initial velocity of that, equal to the mass of rock 1 and its final velocity plus the mass of rock 2 and its final velocity. And this is what we're trying to solve for, which is this V2 final right here. So if we have solve for V2 final, we're going to have everything on our left. So MR1 times V initial plus MR2 times V2 initial. And then we're going to subtract this one right here. So minus mass of R1 times the velocity of the final of rock 1. And we're dividing that by the mass of rock 2 because we're trying to solve for the velocity. So then if we plug that in, it's going to be equal to the mass 1 is 3 kilograms times the velocity plus the mass of rock 2, which is 13, times this velocity minus the mass of rock 1 again and its final velocity. So these are both initial velocity. This is a final one, and we divide that by the mass, which is 13 kilograms. When we do that, we end up with 4,060 in the x, negative 5,180 in the y, and 2,400 in the z. But we have to still divide this by the mass of 13. And when we do that, we get a final velocity of 312 in the x, negative 398 in the y, and 185 meters per second in the z. So with this answer, we can find the change in eternal energy of the rocks. So first, our system is going to be both the rocks, rock 1 and rock 2. So we know that work is equal to the change in energy. We know that work is going to be equal to 0, which is going to be equal to the change in kinetic after the collision plus the change in kinetic before the collision plus the change in energy, which would be thermal because the rocks are rubbing together. So the change in thermal energy is going to be equal to the negative kinetic of the rock after the collision of rock 2 minus rock 1, and then minus the kinetic of rock 2 before the collision minus the kinetic of rock 1 before the collision. So when you do that, you get negative 1/2 mv squared minus 1/2 mv squared minus, excuse me, 1/2 mv squared minus 1/2 mv squared. And we know that this is after the collision and this is before the collision, and that's going to be equal to the change in thermal. So then we plug everything in. So 1/2 times 3 times the velocity minus 1/2 times 13, which is rock 2, times the velocity. And these are after the collision, so this is the final velocities. So we use what we had here, right here, and then we subtract that, and by everything from the initial of the two rocks. So 1/2 3 times the velocity minus 1/2 13 times the velocity. And all our velocities are squared. I forgot to mention that. And so when we do all that for the change in kinetic after the collision, we get 5.0269 times 10 to the 7th. And for the kinetic energy before, we get 4.657 times 10 to the 7th. So when you subtract that, you get a final change in energy of 3.699 times 10 to the 6 joules.